Hey everybody, welcome to another show. Mr. Viteri. Let's get to it. We ended our last lecture on the atmosphere, and let's continue with our discussion on the atmosphere now. So here's another diagram of the layers in the atmosphere, and it's so weird when you really think about layers in the atmosphere. I mean, they're gases, and what differentiates one gas from the other? Now, you could think of it as density. Like if I poured oil and water in a graduated cylinder, you would see that the oil rises above and it's going to sit on top of the water. Well, similarly, the gases in the atmosphere kind of sit on each other. And that's why we're able to determine the different layers of the gases. Okay. So that's one thing that you need to understand. They're pretty much don't mix too much between different layers, and that's why they behave differently in relevance to how sunlight affects their temperature. As we go up in the troposphere, it gets colder. As we go to stratosphere, it gets hotter. Mesosphere, colder, and then thermosphere, it gets hotter again. This could also give you an understanding of how the northern lights work. And so the northern lights are going to be uh, these beautiful skylight things, typically seen at the poles. And why are we seeing this in those areas? Well, the density of the gases that are there and the gases that are there are going to make light behave differently, either reflect, absorb, or transmit differently. And what we pick up from a visible light is going to be the response to those gases. Okay. So understand that they're just sitting on top of each other. We got some vocabulary here: troposphere, tropopause; stratosphere, stratopause; mesosphere, mesopause; thermosphere, thermopause. They could also call that the exosphere, typically all the way out there. And it's going to get really cold as you get into outer space because you don't have the insulation of the greenhouse effect and you don't have the heat of the earth that's trapped in the core as well. Okay. So it's very cold out in outer space unless you get really, really close to the sun. Now, another thing you need to understand is how gravity works. What's weird is that the closer we are, well, let's think about outer space. In outer space, you're pretty much floating, right? Um, but if we are close to Earth, we kind of our feet are close to the Earth. What's weird is that larger objects have more gravitational pull than smaller objects. So the sun is much larger than us, planet Earth. In essence, the sun, we're caught in its gravitational pull. We're getting closer to the sun. Very small, a little bit, kind of, sort of. Um, Let me try to give you a better analogy. If I'm 220 pounds versus let's say another student is 100 pounds, and let's put like a feather in between us, um, and let's just say we were both floating in outer space, where would the feather go? Well, the feather's probably going to be more attracted to me because I'm larger and I'll have a larger gravitational pull. Okay, so gravity is stronger, if you will, closer to an object as opposed to farther from an object. The farther you get away from something, there's going to be less of an attraction. The closer you get to something, there's going to be more of attraction. I typically bug students out by going really close to them now, and I ask them, "Do you feel the attraction now?" And the closer you get to someone, the more you're attracted, or the closer an object gets to something very large, there's going to be more of a pull to it. So that's going to make sense when we talk about the troposphere itself. Closer to the Earth, there's more gravitational pull. Closer to the Earth is going to be where the most dense gases are. Typically, this is going to be the area that has most of the air molecules, if you will. They're still air molecules, they're still spread out, but that's the most densest layer of gases. And so that could help you understand how the greenhouse effect or the greenhouse gas layer is in the troposphere. As you start going into the stratosphere and the mesosphere and the thermosphere, you're getting less dense of gases. Last analogy. I don't know if you ever watched a Superman movie, but sometimes Superman flies into outer space, or if you ever saw like a spaceship coming in to space from outer orbit. Sometimes you see it go on fire, then you see it get turn into ice, then you see it go into fire again, and then you see it to go into ice. Well, what's happening? It's penetrating through those layers of gases. Okay, and the temperature is different in those layers of gases because those gases behave differently depending on the density of those gases. All right. Okay. Hopefully you understood that. Let's keep going. Now, the troposphere is where weather and the greenhouse effect occurs. The next important layer is the stratosphere. The stratosphere is going to be a layer of gas that lays on top of the troposphere. The most important thing you need to understand about the stratosphere is that this is where the ozone layer is located. Speaking of ozone, its chemical formula is O3. What? O3. What? O3. What? O3. Okay. Three oxygen atoms stuck together. Now, we've probably heard that the ozone layer protects us from UV radiation. That's not good enough for the AP exam. You need to become experts. Okay. Um, and specifically, it protects us from ultraviolet radiation. But there's three different types of ultraviolet radiation. There's UVA, UVB, and UVC. UVA comes right through the ozone layer, and to much effect, it doesn't really affect us. Actually, probably sometimes it's good for us. Some people say that sunlight is good for us, and some people say it's really bad for us. But for the most part, UVA comes down on Earth and doesn't really cause that much damage. UVB though, UVB, that is the cause for skin cancers. That's the cause of frogs dying in lakes and ponds. UVB radiation is the most dangerous radiation of them all. UVC hardly even reaches Earth, so we don't really even have to worry about that. All of these radiations come from the sun. They don't give off heat. This is just like a wavelength of energy. Okay, it's a wavelength of energy. It's not like hot. It's not like, oh, it's hot, so therefore the UVB is stronger. No, this is totally different from that. This is a different type of radiation. And once again, I'm trying to clear up the misconception of global warming and ozone layer depletion. This is not that. Okay. Another common misconception is like there's a hole in the ozone layer, and that's what it's said. I mean, that's what's said commonly. But have you ever tried to put a hole in gas? Makes no sense. How do you put a hole in gas? Hold on right now. If, if I pulled this gas down, it's going to get filled with new gas coming from somewhere else. That's the way gas behaves. So, what are they really talking about when they say that there's a hole in the ozone layer? Okay. Well, when they say there's a hole in the ozone layer, what they're really meaning is that there's a thinning of that gas layer, which then allows more UVB radiation to penetrate through to cause the damages that it causes. And once again, those damages are going to be skin cancers, typically in people who have fairer skin. It could destroy foliage, it could burn tree leaves. That would be horrible because it could kill crops. And it typically, one of the early indicator species that tell us that UV radiation is causing a problem is frogs. Frogs don't really have a thick skin. They have a very thin skin that's sensitive to UVB radiation. So they can die if a lot of UVB radiation comes through. So now let's try to explain that thinning. Well, this is kind of difficult. So put on your thinking caps, hold on, and you're really going to learn this stuff. You've probably heard of CFCs, chlorofluorocarbons. And chlorofluorocarbons, CFCs, have the ability of turning O3, ozone, back into O2. What's weird is that O2 plus O turns right back into O3. So think about this as a constant chemical reaction of O2 plus O forming ozone, and CFCs, the chlorine specifically, breaking down the O3 into O2 and O and ClO. So as we had used a lot of CFCs in the past, The CFCs started to break down ozone faster than it could be repaired. Therefore, this allowed more UVB radiation to penetrate through and do the damages that it caused. It increased skin cancer rates. It killed frogs. It destroyed crops. Specifically, this became a really big problem in Australia because that's where the hole typically is. It's typically closer to the poles, the holes. All right. The reason being is that CFCs in the wintertime get locked up. They don't really become reactive, but in the summertime, they're free to do the damage and then they destroy the ozone. That's very heavy. You might want to pause this, rewind it, and take it back. All right. Once again, I'm not talking about temperature increases. I'm just talking about radiation. So let's try to summarize what we just got here. UVA, not a problem. What's the dangerous one? UVB. What does it cause? Skin cancers, frog deaths, foliage destroyed. All right. What is the chemical formula for ozone? O3. How does O3 even form? O2 plus O equals O3. And what destroys ozone? CFCs, which are chlorofluorocarbons, and chlorine actually has the ability to break the bond between O3, OOO. It actually converts O3 into O2 and O. Okay. So the other question is, well, where are these CFCs and why are they in our world? Well, first of all, they are strictly anthropogenic. That means man has made them, or woman. We created this chemical. And we used to put it in propellants. We used to put it in refrigerants because it was a very stable compound and it would not break down. It does not break down, and it worked really well. So if you imagine if you're putting glue in a can like hairspray, glue, and you want another gas in there that could propel it out, but you don't want that gas to mix with the glue. You want something that's relatively stable. Enter the CFC. So back in the 60s, we had a lot of CFCs into most of these products because they were just so darn stable. They didn't break down. They had a long, long shelf life. But what we did realize is that these CFCs were destroying the ozone. And so then we banned CFCs using something called the Montreal Protocol. All right. This all occurs in the stratosphere. All right. Here's another image of what we're going to see that the ozone layer does for us. So this is going to be all the different rays that come from the sun. Infrared, this is the hot stuff. Infrared, this is what causes the heat. Visible light, that's what we get to see, and that's going to be wavelengths between this. UVA penetrates right through. Notice UVB. UVB typically is going to be absorbed by the ozone layer. Okay. UVB will be mostly absorbed by the ozone layer. Now, UVC, it hardly even reaches the Earth. Thank goodness for the ozone layer. Without the ozone layer, we would all be dead. Now, remember how I was telling you closer to the Earth, there is a more dense gases. That makes a lot more sense now. Let me add to that. Since the gases are so dense, at sea level, we're closest to the Earth, there's the most oxygen that you're going to typically get. Uh, high capacity, high quantity of oxygen. So imagine me climbing Mount Everest. If I'm going higher in the atmosphere and I'm getting away from the Earth, if you will, the gases become less dense. It's harder to breathe at the top of the mountain. Right? That's why people who climb these mountains have to wear oxygen masks. All right. Speaking of gases, let's look at the composition of our atmosphere. Now, typically, nitrogen is the big boy. That big boy, big girl, big girl, big girl. 79% nitrogen, 20% oxygen. Some books will say 19. 1% all the other gases. How crazy is that? 1% all the other gases. So once again, if we were looking at the composition of the entire atmosphere, 80% nitrogen, 20% oxygen, 1% all the other gases. That means if I farted right now, how much percentage of of fart is in the atmosphere at one time? Well, that's methane, and methane is going to be under 1%. All right, sorry to give you all that. How about carbon dioxide? Less than 1%. All right. Now, pay close attention to this because we're going to go towards the greenhouse effect, and I want you to become masters of that. Now, we're going to talk about the greenhouse effect, but you need to understand some greenhouse gases, also known as GHG. Now, there are three that you need to know specifically. H2, the ISO, H2O, that's the most abundant greenhouse gas. However, we don't necessarily equate that when we're talking about global warming because it's kind of like a standard. You don't want to get rid of water. It's not like we want to decrease the amount of water that's in the atmosphere. Okay, water is a great thing. Okay, now CO2, that's the big one that we correlate global warming with and the greenhouse effect. All right. Now, CO2, we make CO2. I'm making CO2 as I exhale right now, and the plants outside are absorbing CO2. So, why isn't it just like a net zero, meaning that there is no added to the atmosphere? What will tell you, what science tells you is that we're burning stored carbon dioxide or stored fossil fuels, and our plants or our photosynthetic organisms aren't absorbing enough of it. So, therefore, our CO2 levels are going higher and higher due to the studies and accounts that they do. We have another gas called methane. And methane is going to be the chemical form of CH4. That's going to be caused by the breakdown of organic material made by microbes. Have you ever been to a lake or a pond and maybe you threw a rock in the bottom and you saw little bubbles go? Blah, 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 blah? Well, that's typically methane escaping. Methane can come from many different areas. Um, like when you pass gas, some methane can come out that way. Um, Methane is very flammable. It is 10 times stronger at capturing the sun's rays than CO2. A big thing that is quite popular now, might sneak your way up into the AP exam, it's about 3 years old, this data now, is that cows produce a lot of methane. And so there is a push to stop our consumption of cows because they're eating corn as opposed to grass, which makes them very gassy. And if we talk about the concentration of gas that they can produce over a long period of time, we're talking about significantly rises in the methane content that's in our atmosphere. Ew, cow farts. Ew, right? And so there is a push to stop eating meat or stop eating beef because we raise cows and cows could increase methane. And then that methane is a greenhouse gas that's 10 times stronger at capturing sunlight than CO2 and therefore causing the earth to even warm more. All right. All right. We'll end it at today on that discussion.